seeing the universe in infrared. So, what is the Spitzer telescope? It's the final of 4 space-based observatories in NASA's Great Observatories program. The overall mission is to see the entire universe for the entire light spectrum. We have the visible light by the Hubble Space Telescope, Compton sees the gamma ray, Chandra with the X-ray, and then ours, Spitzer, was tasked with the mission to detect and observe infrared radiation, which is primarily heat radiation, from the early universe, distant galaxies, and newly forming stars and planets. It uses this infrared light to detect objects that are behind dust clouds, or too dim or too cool to see otherwise. So this has been a new concept. The American astrophysicist Lyman Spitzer Jr., who it's named after, actually proposed putting the observatory into space to avoid the blurring effects of Earth's atmosphere. This was in 1946, 12 years before NASA. This effort led to the launch of Hubble, and ultimately the telescope named in his honor. After ground-based and space-based observations in the 80s proved successful, the mission was introduced. Originally, they would be launched with the space shuttles, but unfortunate events caused setbacks and redesign. After the Challenger tragedy, items like telescopes were no longer permitted to accompany the space shuttle into space, so they had to be refitted and redesigned on expendable launch vehicles. Then, in the 1990s, NASA's budgets were cut even more, and the launch time was pushed back even further. This time will lead to many advances in astronomical technology, though, benefiting somewhat. There's lighter metals that can be used, which cut down on the overall mass and weight of it, and the new innovative orbit that we'll talk about a little bit later that would cut down on cost and overall mass. So it was finally launched on August 25, 2003 from Cape Canaveral Air Force Base in Florida. It was designed to last a minimum of 2.5 years. This initial phase lasted 5.5 years, thanks to the ingenuity of the scientists, before transitioning into the second phase. And in that phase, it will continue late into this decade. So Spitzer's technology. Its main components are the 0.85 meter or 2 foot 10 inch telescope and 3 cryogenically cooled instruments. This is achieved in part thanks to the onboard liquid helium tank. The system needs to be simultaneously cooled and warmed at the same time. Its 3 instruments need to be kept near 0 degrees Kelvin, because any object that is above 0 degrees Kelvin emits some form of heat radiation. And that could cause interference, which is called infrared noise. So these 3 main instruments. The infrared array camera. This detects light at near and mid-infrared wavelengths, between 3.6 and 8 microns. That 1 micron is 1/1,000,000th of a meter. This is an image of the Black Widow nebula. The next one is the infrared spectrograph. It provides both high and low resolution spectroscopy at mid-infrared wavelengths, from 5 to 40 microns. Now, it takes the light that it receives and splits it into like a prism into a spectrum. And there, since we know that each element has its own signature in the spectrum, it can determine the composition of the objects that it's looking at. And that comes in handy when things like water and carbon dioxide. And the last one is the multi-band imaging photometer. This detects light in the far infrared at wavelengths of 24, 70, and 160 microns. This is an image of the double helix nebula. So after 5.5 years, it exhausted its helium tank, and then it transitioned into its warm phase, where only 2 channels from its infrared array camera are active, and it's refocused on the asteroids and gas giants. This all leads us to Spitzer's positioning in space and its innovative orbit. It's actually an Earth-trailing orbit. It's kind of blurry here, but Earth is up here, and it drifts away from Earth at 1/10 of an astronomical unit per year. This has benefits also. It avoids Earth's heat interference, that infrared noise, and it allows it to stay in a cooler environment. It allows it to take less helium to cut down on the weight, and it also used less helium at a slower rate, which allows it to extend its lifespan. So, Spitzer's discoveries. The first telescope to detect light from an exoplanet. That's a planet that orbits a star outside of our solar system. This is a heat map of exoplanet HD 189733b. It's located 60 light years away in the constellation Vulpacula, also known as the Fox constellation. It's observed stellar nurseries, where stars are born and solar systems evolve. Astronomers refer to this as Rho Ultra. It's one of the closest star-forming regions to our own solar system. It's detected quasars, believed to contain light from stars that formed as early as 100 million years after the Big Bang. That's the red blob there. So it's almost looking back in time. Our own Milky Way galaxy would be a good example for the Spitzer. We would be able to see all the stars that are hidden behind all the clouds and dust and debris. So what's the significance of all this? The Spitzer can trace the chemical history of evolving planetary systems and provide statistical evidence for planetary system formation. And then it can analyze these for the planet's compositions. This could help with future planet-searching missions to know the most likely places to look. And also, these findings may hold the secret to discovering life on other planets and finally answering the question, are we alone in the universe? Thank you.